He was gonna record the lecture.
Hi, good morning, everybody. So, is there anyone who have not taken the exam yesterday? Everyone has taken the exam? Good. Have you seen your score? It's already visible in the score. Okay. All right. So I think most of you guys have got a very good score. Congratulations. Many of you have scored perfect, like 10 out of 10. Very, very good. There might be few people who may not have scored that high. So it's okay. It's the first classes. Maybe it will take a little bit of time to get used to it, and we'll discuss. Okay. So if you have some questions, I recommend you to come and visit me in my office hour. Again, my office hour is Thursday from 2 to 4 p.m. If you think that time is not suitable for you, talk to me, and we can find some other time. Okay? All right. So, let us try to remember what did we discuss yesterday. That means right before the exam. Can anyone remember what did we discuss?
If you have an antenna in your hand and you're inside of a building, all the interruptions that you might go through.
Right. So we talked about the electromagnetic interference or interruptions that may come from lots of stuff around your room. For instance, one of the most strong electromagnetic interference or disturbance may come from these electric lines, right? The cables. What are some other stuffs? Those could be the antennas. Your computer has a lot of antennas. It has Bluetooth antennas. It has GPS antennas, right? What else? So, and we talked about the following. We say that those electromagnetic interference, let's say that we're talking about the cables. So the cables can be thought of as a long wire and if you want to find out its impact on some point P at a distance D, then the electric field at that point P would be twice A rho L, and the denominator would be D. Okay? So if it is a long, very long wire, then this will be the corresponding electric field. And we also discussed yesterday that if it is not a long wire, if it is a finite wire with the length of twice L, if it is twice the length, then the electric field can also be determined by changing the limit of integral. So, for a long wire, we take the limit of integration to run from minus infinite to plus infinite. In case of a finite length, we can change this limit. We can say that it runs from minus L to plus L if the total length is twice L, right? And we also say that in those cases, you will find that the electric field for a finite wire length is twice K rho L divided by D, and if you plug in all these limits, you will eventually find out that the limit gives you an extra factor L divided by root over D square plus L square. So I'm not doing this stuff for you. I believe you can do it yourself. So the basic thing that you have to do is instead of taking a minus infinite to plus infinite limit, put a finite limit, okay, and do the integration. If you cannot do the integration, let's say that you somehow forget how the integration is done, then there is a way to help you a little bit. Let me see if I can show it to you. So I know that sometimes doing calculus or integral equations is a little bit difficult. You might not remember everything. So there is a tool that may help you to do integrations. Okay? Have you used this guy? It's called Wolfram Alpha. It's there is one version which is offline. It's called Mathematica. And I think Mathematica is available for all of you guys in UNC Charlotte. You can use it free of cost. And Wolfram Alpha is the online version of it. It's a limited version. Mathematica is more full though. So, but the basic idea is that if you utilize those tools, then you can use them for doing some integration. Let's say that I'm doing a simple integration. What should I write? So I'm trying to integrate the function sine of x in the limit of 0 to pi. Okay? Let's try this. If I integrate sine x in the limit of x running from 0 to 2 pi, that means I'm trying to integrate the function sine x. This is 0, this is pi, this is 2 pi. Everyone can see it? If I integrate from here to there, what is the result? If I integrate the entire term, integration means I'm just adding up all these areas. So if I add all the areas, what will be the total result? Say it again? 0. 0. Everyone understand? Because both of these areas are equal and opposite in size. So the total of them is 0. Okay? So if I integrate sine x from 0 to 2 pi, I expect that the result to be 0. And this is what it says. It's 0, right? What if I integrate from 0 to pi?
1.
Pardon?
1.
1. And if you change the integration limit, that will tell you. So is that correct?
It's 2.
It's 2. It's 2. Okay? But that's okay. Don't worry about it. Because I myself forgot about it. Okay? So I wanted to show this stuff to you so that you can, even if you forget that how to calculate, you can always go and look at here. Okay? You can also use it in your exam. I mean, in my exam. Okay, not other exam. Okay. It's only for electromagnetic course that is taken by me. Alright, so that's why I may skip from time to time the detailed analysis of calculations, okay, through calculus. You can always find it out. Alright, so let's go back to the blackboard. Okay. coming back to our discussion, original discussion, we say that if the length is finite, then we are going to change the limit, and based on that calculations, we'll get an extra factor, L divided by root over d square plus L square. So L is half of the length of the wire, and d is the separation between the wire and the point where we are trying to calculate the electric field. Okay? So I said also yesterday that if this guy, this point P is very close to the wire, very, very close. That means if d is very, very small compared to twice L, let's say if d is very, very small compared to L or twice L, then can you check how this equation will turn up? If I take d to be very, very small compared to L, then you can ignore this term, right? So d square plus L square is pretty much similar to L square, right? So if I cancel out, if I ignore this d term, then what do I get?
1.
1. Just 1. So that means if d is really, really close to the wire, then even if the wire is very short, even if the wire is not too long, you can still consider it to be an infinite wire. Right? Yes, go ahead.
Just a question. What are we integrating and protecting where you got the L1 and square root of d squared plus L?
So you want to know what is the function of
Cosine
sine?
beta? Is it the cosine beta?
It is, absolutely, yes, it is the cosine theta. So if I use theta instead of y, then I have to change this variable. So instead of y, I will write theta to be running from 0 to tan inverse L by 2. Okay?
Okay.
And then,
Cosine beta, and that gives us the L1 and square root.
right.
Got it.
Okay. And then you can use the tool to find out the exact value. So you got the idea that if we take the value d to be very small, if we take the point very close to the wire, then even if the wire is finite, you can still use the equation of infinite approximations, and you will get the right result. Right? Now the question is, like at what point of time we would say that no, we cannot use the infinite integral, infinite approximation anymore. I understand that if d is very, very small, we can use this approximation. But at what point, at what value of d, that approximation is no longer valid. That question can be answered if you look at the relation between them. So it's actually not d, but it is d square and L square that matters. Okay? So really, what matters is whether d square is much, much less than L square. And a good idea is to always check whether this d square guy is at least 1/10 or even less than L square. Okay? So a practical viewpoint says, let's say if L is 10 meters, okay? Then I expect that d square must be less than 1/10 of L square. Okay? Where does this number come from? This 10. This 10 is just a practical number. Okay? So engineer always use some numbers from their pocket. And a good idea is always check that whether, when you say that something is very small, we typically mean that whether it is small by a factor of 10 or by a factor of 100, something like that. Okay? So if we say that d square is smaller than L square by a factor of 10, that means d should be less than or equal to 1 over root over 12. Right? So now you know that at what point you can use this approximation of infinite wire, and when you should stop using that infinite approximation and use the other equation. Okay? Alright. So everybody is clear at this point? Good. Right. So let us try some brainstorming. Let's say I had this wire which had a length of 2l, and I'm trying to find out electric field at a point P at a distance d from the wire and then I cut the length by half. Okay, so I take out this part of the wire. I also take out another part of the wire, so that the total length reduces by half, by a factor of 2. So in that case, what would you expect the electric field to be? Would you expect the electric field to increase or decrease or remain the same? What is your guess? It decreases? How do you know that? Very good. Very good. So the formula already talks about that. What is the impact of L? Right? So it says, if I say that L is going to be reduced by a factor of 2, then all that you need to do is to take this equation, and I don't care about this guy, 2k rho LD, because they are going to be remaining same, right? So don't worry about this guy. Just think about the other factor, L divided by root over t square plus L square, right? And so if this guy changes, instead of L, if I write it as L by 2, D is going to remain the same, and L will be replaced by L by 2. Now you just figure out that whether the new electric field, so let's say this is E naught and this is E new electric field. Okay? So E new divided by E naught. New means when I change the length from twice L to L, then the corresponding electric field is denoted by Dn, and E naught is the original electric field when the length was twice L. So En by E naught would be what? Half divided by right? So that will be the answer. Okay, I'm simply taking the ratio between the previous electric field and the new electric field. Okay? All right. Now let's look at another possible case. Let us say that I find out I have some electromagnetic interference coming from a piece of wire. Let's say that you are working in a table and the device is plugged into the power socket. So a long wire is running through it, okay? Running beside it. So these wires could be a source of electromagnetic interference. Okay? So in order to reduce this electromagnetic interference, maybe you come up with an idea that what if, instead of having a long wire, actually try to fold it down, make it very small. Would it reduce the electromagnetic interference or not? Can we tell from this equation whether it would help us or not? Let's see. So instead of having a very long wire, let's say I take the previous wire, but instead of cutting it down, I fold it. So I had previously a long wire, and now I fold it down. Okay? So the total length would be twice L, and the question is, if I take a point P at a distance D, how the electric field is going to change? So before we do the calculations, let us see whether our common sense can find out that answer. So what is your best estimate? If I take a long wire and squeeze it down to a very small point, would the corresponding electric field reduce or increase? Or remain the same?
Increase.
Increase? Why?
Charge density.
Charge density? Very good. Very good. So you're saying that if I squeeze it down, the charge density, the effective charge density would gonna increase. Why? Because if I fold it down, let's say I fold it by 2, okay? I just fold it into half. That means the charge density, effective charge density, is gonna go up by a factor of 2. Right? So previously, let's say it is a charge density of rho L. If I fold it down to half, then instead of rho L, the charge density would be twice rho L. Right? If I make it another twofold, then the charge density would be what? What is the charge density? If I fold it by another, by
4.
4. Right? So it will go up like that. Okay. So rho L go up. Understood. That's why your assumption is that electric field would also go up. How about L? This guy go down, right? So if rho L goes by a factor of 2, L comes down by a factor of 2, what will be the net result? If L reduces, we understand that the electric field also reduces, right? That's what this equation tells us. Right? So if I fold it down, then most likely it will have two different impacts. One of the impact is rho L, the charge density would go up, but the length go down. That may cancel out, or that may counterbalance the electric field impact. Okay. So let's take the most extreme case, when I squeeze the entire electric wires to a very small point. Okay? I squeeze everything down to a small point. And in that case, if I have the point P at a distance D, how much electric field would there be? You take this entire guy, squeeze it down to a point, and try to calculate the electric field from here. What will the electric field be? Can anyone tell?
K QQ over.
Go ahead. K? Go ahead.
Charge of the point times the charge of the total charge of the wire divided by the distance squared.
Right. So what will be this Q?
The rho L divided by L.
No, the other way, rho L multiplied by L. I'll multiply by twice L. Okay? This initial length is twice L. So what we're saying here is that if you take this long piece of wire, reduce it down to a point, then the total charge is not going to change, right? Total charge is always the charge density multiplied by the total length. So the total charge is not going to change because we are not taking out any charge from this wire. The rho L is of course going to change, but the total product of rho L and the length is going to remain same. So I'm just using the basic Coulomb's law, and basic Coulomb's law says that electric field is going to be proportional to the charge, total charge, divided by d square. Right? Total charge divided by d square. That's exactly what I wrote. So this is the interesting part here is when electric field was calculated for a point charge, then it is proportional to d 1 over d square. Whereas if the length was expanded, if I take a long wire, then it is proportional to 1 over d if we take L to be very, very large compared to d square. So why one is proportional to d square and the other guy is proportional to d? Let's try to understand this. Wow, you don't have any duster here?
over there.
Pardon? Is there a duster? Okay, thank you.
Doesn't really, it does just kind of spread the dust.
Ew. I wonder how long this thing's taking for. You should put it on top of this.
So let me write the expression one more time.
It's really knocked over the gate in the CRI deck. It's like the yellow on thing. Oh, knock it over. When? Well, I wasn't there when I got there this morning. It's working.
That's what I discussed, right? So for a wire with length L, electric field will look like the top equation, and for a wire that is folded down to a single point, electric field would look like the following equation. Right? Alright. So why there is this much difference? One depends on 1 over d and one depends on 1 over d squared. So to understand it, let us look again the wire and see how the impact is at a point P from any segment of the wire. So if we take a small segment from this wire, we'll see that the electric field is somewhat angular to the x-axis, right? And we will also find a mirror segment from another part of the wire, which will also have a similar magnitude of electric field, but this time it will be directed in such a way so that they cancel out their y component. Right? So these guys are going to cancel out their y component. And that's why the total electric field that they will produce is actually less. Okay? However, if they were not a long wire, but they were squeezed down to a single point, then all of their electric field will be directed along the x-axis. So there will be no y component. Right? So in that case, what do you expect? Would the electric field go up or go down? Go up. Because previously, when the wire was extended, there was y component that's coming from two mirror segments, and those y components were being cancelled out. As you squeeze them down, make them a point, not an extended wire, then there is no y component. All the electric field are going to be directed along the x-axis. So the total electric field is going to go up. Okay? So always remember that. So the point I'm trying to drive is this, that if you find out that your electromagnetic interference is coming from a wire, maybe it's running from a cable, do not try to squeeze it down and say that, okay, all my problem will be gone. No, you will make it worse. Okay? You will make it worse. And why you will make it worse? Because there is no more y component. They are going to cancel out. All the components are going to add up, simply add up. So the total electric field will increase. Okay? All right. Let us say that you are working with a device, you are doing some experiment, and your experimental setup is on a table. So let me draw a cartoon of a table. And your device is up here. Okay? Let's say this is an antenna that you are trying to test. So typically, engineers say that this guy, which you are testing, is a device under test, DUT, duct. Okay? So duct is a common electrical engineering term. Don't get surprised if you go to an interview and people say that, let's say you have a duct. Don't ask him that what is a duct? That means device under test. Okay? So you have a duct here. Let's put that down. Device under test. Okay? And let's say that the interviewer asks you that my test bench has some wires running behind it. Maybe those wires are some electrical cables that are connected to a plug point. Okay? Maybe I have another instrument. This is also an electrical instrument. Maybe it's also here. Okay? And let's say I have also an antenna. Okay? This is also at one corner of the table, and maybe that antenna is trying to send some signal between two rooms or between two buildings of the room. And you are doing your test here, okay? And your result is not what you expected. You are getting some disturbance. So you're going to find out that what might be the possible source of disturbances. What are the disturbance sources? One source would be the cables, right? One source might be this guy, given that this guy is running, right? If this device is operating, then probably this might also cause some electromagnetic interference. This antenna could be a major source of interference. Okay? So, what might be the biggest source of interference that you can think of? Would it be the cables? Would it be this electronic device? Maybe this is a microwave. Or would it be the antenna? What would be your guess?
Whatever is closest.
Right. Whichever is closest. Right? That's the very first guess you should pinch on. Whichever is closest might be the biggest source of interference. And why? Why you think that the distance matters?
So it's proportional to 1 over d squared.
Right. So Coulomb's law says that it is proportional to 1 over d squared. And that's why if something is closer to my duct, it probably has the biggest impact. It probably is the biggest source of noise. But we learned two different stuff. We learned that force could be proportional to d, 1 over d, or force could be proportional to 1 over d squared. If it is a point source, then force is proportional to 1 over d square. If it's a long wire, then force is proportional to 1 over d, right? So it changes. So let us say that this guy, let me draw some distance information, okay? So let us say that this is 1 meter. This guy is also say 1 meter, okay? And the distance between that and this cable is probably 0.1 meter. Okay? Again, I'm trying to show you the distance between the duct and the other possible source of noise. There are 3 possible sources of noise. One is the antenna, one is this microwave, and one is the wires that is running behind the table. Okay? And I told you that what are the distance between each of them. So which one would you think the biggest source of noise would be?
The wire.
The wire, because the wire has the smallest amount of distance. Okay, but I told you just a moment ago that the wire has actually Y component. Okay, so the Y components are going to cancel out each other, right? But if it's a point source, then probably nothing is not going to cancel. Everything will add up, right? So in that case, this is actually a critical case. In that case, we have a wire. The wire is the closest, but the wire also has a Y component that are going to cancel out, that are going to counterbalance each other. So it might be possible that despite the wire is the closest, it may not have the biggest impact. Okay? So in that case, in order to truly know what is the biggest source of noise, you have to plug in the numbers. Okay? You have to really know what are the charge densities in those wires, what are the charge densities in the antennas, and what are the charge densities in the microwaves. Okay? Until then, you cannot find the exact answer. So you understand that sometimes things become complex. But if you do not know anything, your best bet is the distance. Okay? Whichever is the smallest, whichever has the smallest distance from your duct might be having the biggest impact. Okay? But things may be more complex than that. It may depend on the geometry of the disturbing point. If the geometry is a long wire, then it has one kind of impact. If it is a point source, it may have another source of impact. Okay? So that's why in this course we will be trying to understand the impact of different kind of geometry and how we are going to change the electric field. Okay? So in the exam, if I give you a picture like this and ask you to find out what might be the biggest source of impact, biggest source of electromagnetic disturbance, will you be able to find out?
Yes.
Okay, good. Very good. So don't get surprised and say, oh, where does it come from?
So would the correct answer be it depends on the charge density?
For this guy, yes. But you may have some other values, right? For instance, if instead of 0.1 meter, let us say I write it as 1 meter. So this guy is 1 meter away, antenna. The microwave is also 1 meter away, and the wire is also 1 meter away. Everything is 1 meter away. Which one would have the biggest impact? Let's try this. What is your guess? Everything is 1 meter away. Which one has the biggest impact? Microwave. Why? Go ahead.
It's a high-powered device.
It's a high-powered device. Okay, that's a good guess. What else? What else? Go ahead. I mean, it can be anything.
Scan transformer.
Say it again.
Scan transformer. Microwave transformer.
Say it loud.
Scan microwave transformer.
No, I'm not following you.
He said it has a transformer in it.
Yeah.
Okay. Can you elaborate a little bit further? It's okay. I mean, go ahead.
Well, yeah, that would make sense, right? Because we've got more coiled wires in it, so
Yeah.
it'd be like a compacted charge density. That would be that way. Of all the components that have the highest charge density, which cause the greatest electric field.
That's a good guess, actually. So you're saying that since the transformer has a very high density of wiring, like have you seen the what is inside the transformer? Have you taken a course on it? Electric, like what is it called? energy conversion, or that talks about motors, generators, transformers. We go over the next one. Oh, that's next class.
Yes.
Okay. So you're already experts here.
I think this is the prerequisite for that.
Okay, got it. So these transformers, yeah, you're absolutely right. This transformer can be a big source of noise. Yes. And in fact, if the transformers are very compact, you can consider this transformer a point source. Okay, a point source. But remember that if it is a point source, then maybe there is no component which is cancelling out each other. There is no Y component. Everything is X component, and they are creating a big impact. Very good. So the wire, we know that this wire, they have some Y component. Let's say that this wire is trying to have some impact on this duct. They're trying to create an electric field this way, but it has a middle part of the wire. We are trying to create an impact in that way. So it has both a horizontal component and a vertical component to each other. The horizontal component are going to cancel out, but the vertical component will add up. So the wire, despite they are having the same distance from the duct, it may have a less impact. Okay? This guy might have a bigger impact, or even this guy might have a bigger impact. Okay? Then we need to know the details of it, like what is the charge density here, or what is the charge density here. All right? Okay. Thank you for asking this question. So let us see whether we can find out the electric field for some other possible geometries. Another possible geometry besides the wire is a ring. Okay? So we talked about the wires, and we talked what is the electric field for this wire. What if I take this wire? You all know that this wire has two components of electric field, X and Y. Y is going to cancel out, X is going to add. Now what if I take this wire and make it round? Okay? Make it like a circle, like this. What does your common sense say?
Instead of L, we use the circumference.
Yeah, that's true, yes. So the total L would be the circumference, that means 2 pi r. What would be the impact on a point in terms of electric field? Let's say that we are trying to calculate the electric field at a point P at a distance D, and previously it was an extended wire, but now I take the wire around this point P and make a circle. It's not a perfect circle, but let's assume that it's close to a circle. What is your guess? What's going to happen to that point P? What would be the electric field?
Are they in the same plane?
They're in the same plane.
So are we assuming that P is at the direct center?
Yeah, let's assume that P is the dead center.
Well, then theoretically, all of the electric field forces should all cancel out.
Right. So previously, we only had Y component that are going to cancel out from each other, right? But now, you made it a circle. So previously we had all the X components that were adding up. But now, you have a segment of the wire. Let's say we are talking about the X-axis. We have one segment of the wire, and we have also another segment of the wire exactly at a mirror position. And these two segments would have cancelled out each other's impact, because they are creating electric field onto opposite directions, right? So your guess is absolutely correct, that if P is at the point of center, then most likely all the electric field is going to cancel out at the center, right? What if P is not at the center? What if P is implied? Let's say that P is closer to one side compared to the other side. Let's say P is here, and this is the center O. And P and O are not same. Would electric field be cancelled out? So there would be a net electric field, a non-zero electric field, if P is not at the center. Okay? And what if P is not on this board? What if P is here? Let's say your wire is at the board plane, and the point where you want to calculate the electric field is out of the plane of the board. It is right here. But it is at the center. So if you take a straight line, expand this out, P will fall right on top of it. Would the electricity be cancelled out, or there will be some net electric field? There will be what? There will be very large. I mean, there will be a Z component. It depends on how far they are, right? Now there are two things. One is if we take this point P. Let me come back. First of all, let me understand that if everyone is following that what is the picture here. So we are trying to say that we have a piece of cable, and that cable has a round shape. Okay, it's a loop, and we are trying to calculate an electric field not at the center of the loop, but somewhat away from the loop. Okay? So you said previously that if it is at the center of the loop, then most likely the electric field will be zero, because we have mirrors of segments from any point of these wires, right? Like if we consider electric field from this segment, of course we're going to have a mirrored segment on the other side of the wire, and that's why the total electric field is going to cancel out when we add them up. Now the question is that instead of having the point P at the center, if we take the point P out of the center, the electric field would not be cancelled out, right? There would be some net component. So if we just keep taking this P out further and further away, what would the electric field be? Would it increase or decrease? Decrease. Would it decrease? It would quadruplically decrease. But you just say that if I bring it closer, if I come very close to this center, the electric field is going to be zero. So if I take it out of the center, electric field is going to increase. But you also say that if distance increases, the electric field is going to decrease. So which one is correct?
There must be a threshold.
Yeah.
There must be a threshold, right? So there are actually two things simultaneously happening. Do you follow? So there are two things. One is, if I am directly at the center, then all the electric field is going to cancel out. If I take this point away from this plane, then there will be some Z component. Z means, let's say this is XY plane. So this is X, this is Y, and this is Z. So if I take this point P away from this plane, then we will have some contribution from Z components. So that's why electric field is going to go up, right? But at one point of time, you will see the electric field is going to reduce again, because you are going further and further away from this total object, right? So electric field, if you try to draw the electric field intensity with respect to distance from this loop, you will see that electric field initially increases as you go away from the center, but at one point of time, it's going to come down again. It's decrease, right? So electric field, let's say I'm trying to draw what happens when I take a point P and change its position along these Z directions. Let's say this is the Z direction, and I'm trying to find out the electric field of that point P. Then I'm sure that if Z is 0, let's say 0 means this is the center, where both Z is 0, and let's say this is also XY component. XY is also 0. If I take Z to be non-zero, then electric field is going to go up, but maybe at one point it will again go down, right? So there might be a point where electric field is maximum. Okay. So just look at that. I simply, what we are using is simply Coulomb's law. And Coulomb's law says that if you take something away from from a charge, then its impact is going to reduce by a factor of 1/d squared. But that simple formula, when you are trying to apply it on different geometry, you are getting very interesting results. Very non-trivial results, right? This is exactly what we are trying to drive at. When you began this class, maybe you were already familiar with Coulomb's law, and you knew that Coulomb's law says that force decreases proportional to 1/d squared. But now you know that it might not be that simple. It really depends on what kind of geometry you are talking about. Okay? The answer could be very critical. It depends on what is the geometry, how far you are from that particular object. Okay. So let's try to figure it out, that how much electric field could there be for a circle of charge. So we will try to figure out the electric field for a ring of charge. Okay? So let's say that this ring of charge also has a charge density of rho L, and let us also say that this ring has a radius of V. Okay? Before we go and start doing the calculation, let me ask you some basic questions. It's coming from some high school mathematics. So if I want to find out the length of an arc, let's say this is an arc, and the arc creates an angle theta at the center. Okay? And we know that the radius of the circle is V. The angle that is created by the arc on the center is theta. Can you find out what is the length of this arc from these two relations? Do you know there is a relation between the length of arc, length of radius, and the angle theta? Does anyone know? It's okay if you forget. So the relation is the following, that let us say that this is L. Okay? L is the length of arc. So V theta is, the V multiplied by theta would be the length of the arc. Just basic high school mathematics. It's okay if you forget it. So we'll be utilizing this relation in our next step. Just let me write one more step here, that if we take the derivative of this equation with respect to theta, we will get V proportional to dl d theta. Okay? We simply did the differentiations of this equation with respect to theta. So this guy, if I make a differentiation with respect to theta, just take this guy and this guy, we get the following point. Okay? So we'll use these equations later on in our calculation. Let's begin the actual electric field calculation. So we have an object which is a circular wire, and we're trying to find out the electric field at a point P, which is having a distance, let's say h. Okay, so this is xy plane, this is x-axis, and this is z-axis. Okay? And we're trying to find out the electric field at a position with the coordinate of 0, 0, h. Okay? So h is the z coordinate of this point. And the wire has a radius d. Alright? Now how we are going to calculate the electric field for that piece of circular wire? Let's see. If we try to calculate the impact of a small segment on the wire with a small length dl, and try to find out the Coulomb force for this small segment into the point P with the coordinate 0, 0, h, what would be the value of that electric field? The electric field will be proportional to K multiplied by the charge in that small segment of wire. Right? So what is the charge in that small segment of wire? If the total wire length is 2 pi d, of course, and the charge density in that wire is rho L, the charge in that small segment is going to be rho L multiplied by dl. Right? So rho L multiplied by dl. That's the total charge in that small segment. Okay? And we are going to divide them by the distance between the point P and the small segment. So what is the distance? If you know the particle distance is h, you also know the radius of the circle is b. What is going to be the distance between this small segment and the point P?
Square root of h squared plus b
B
squared.
square plus h square. So instead of b square, I'll write it b square plus h square. That's d. But we have to write d square. So we have to take out the root over, right? There won't be any root over. Are you following? Because it is the square of the distance. So instead of writing square root of d square plus h square, I just write simply d square plus h square. Okay? So that's the contribution of a small segment on a point of P. Now, tell me this. If I have a segment here that's having some contributions of electric field at the point P, I should also have a mirror component somewhere there. That would also have an equal magnitude of electric field, but that will partially counterbalance the other electric field. So let's say this is also dP2 and this is dE1. Then these two guys is going to cancel out their x component. Right? They're counterbalancing each other with the x component. But they have also another component in the z direction. These are going to add up. Right? So, when we will add all this electric field, we are going to ignore this x component because we know that this x component is going to cancel out. We will only take into account the z component part of it. Okay? Now tell me that how are we going to only consider the z component? We need to multiply this guy by some other term. Okay? So how we are going to do this? Let's just find out what is the x component and what is the z component here. Okay? So this guy, if you divide them into x and z component, we have to write it this way. So you have a z component and an x component. And the coefficient of z component would be, let's say this is theta. Okay? Let's say this guy is theta. So the z component would be cosine theta multiplied by z hat, and the x component would be sin theta multiplied by z hat. Is everyone following? We are dividing the electric field into two different components, z component and x component. And the idea is that eventually we will just drop the x component. We will only consider z component. Now, the thing is that how we are going to calculate the value of theta. Can we find out the relation between theta with h and b? Is it possible? Do you see that theta is actually same if we write it in these directions? Right? These two theta are same. And we can use trigonometric relation. We can say that tan theta is equal to b over h. So, tan theta is proportional to b by h. Right? So we can also know what is cos theta and what is sin theta. Right? We don't worry too much about this x component part, so let us just find out what is cos theta. Cos theta is h divided by b square plus h square. Okay? Is everyone with me up to this point? So as we said that the x component is going to cancel out. So we will only consider the z component part, and then we will add them up. So the d component, let me write it as just z component, is going to be k rho l dl b square plus h square, and then we multiply them by cosine theta. And we know that cosine theta is just h divided by root over b square plus h square. Right? All right. So the total EZ would be an integration of the right hand side. So here k, rho l, h, b, they are all constants. So I take it out from the integration expression and I keep only something that is variable, that changes as we integrate over the entire circle. So the only variable here is dl. Okay? So now how we are going to assign the limit of integration? Remember that dl, we just talked about it a little earlier, that dl and b and theta, they have a relation. Let me actually, instead of theta, let me change it a little bit. Let me write phi. So the previous equation, instead of theta, let me write phi, because I have already used theta in my equation. So I don't want to confuse you guys with two different theta. So one is phi, okay? The phi is the angle created by the arc on this circle. Okay, let me write it, phi. And theta is the other angle that one small segment of the wire is creating on a point P. Okay, so these two angles are a little bit different. So let me just use this formula that dl can be replaced by b multiplied by d theta. So instead of dl, I can just write it as k rho l h b square plus h square 2 by 2, and we can write it as b phi. Okay? And the limit of this integration is run from 0 to 2 pi. So eventually, you will get the following. You will get k rho l h b square plus h square multiplied by twice pi. Alright? You can take a picture also. If it is just take a picture, or you can also find it out in the book. It's also fine. Okay? So what I'll give you a minute to finish up, and then I'll conclude the class.
Just to clarify, that's a multiplication symbol.
Which one? Yes, this is my. Oh, okay. Let me just take it out. Otherwise, you would think that it's not an X. Thank you for finding it out. It's a multiplication. Done? Okay. So you can also find it out in the book. If you miss a point or two, it's absolutely fine. Consult with your book, you will get a very clean picture. So in my class, I will try to cover what is discussed in the book. And if you miss something, you can always go back and look in the book. There are also a lot of resources in the internet. You can also consult it. But there are some stuff that I'm afraid may not be there in the book. Okay? For instance, when you talked about what happens when you take a long piece of wire and cut it into half, or what happens when you take a long piece of wire and fold it into half, or squeeze it down to a point, What is the impact? Which impact is larger? Which impact is smaller? Those kind of stuff may not be fully discussed in the book. Okay? So I would ask you to pay very special attention to those things because those are very important. Okay? Your questions, I mean, in the exam, I might ask you a question or two from those topics, and I hope you will be able to answer it. So even if you miss something, I highly recommend that you consult with your peers and see that what you are missing. Okay? You talk to them, you come to me, and we can also talk further. All right? So the basic idea is to just prepare you as a better engineer. You understand that you can definitely do a lot of math and try to solve a lot of exercise. But still, when you will be out there as an actual engineer, professional engineer, you might be feeling that, oh, I have not learned anything. So I don't want you to feel like that. Okay? I want you to be enough prepared. You really should know that this is the stuff that I learned. Okay? You may forget some details, that's okay. But you must not forget some bigger picture. Okay? You may forget all these equations. That's totally fine. But at least you should know that why different kind of geometry have different impact in terms of electric field. Why the impact are changing? We talked about, right, that if you take a long piece of wire, it has one kind of impact. If you squeeze it down, it has another kind of impact. So you must not forget this kind of stuff. Okay? The calculations, these are details, and you can always look it up in the Google. All right, thank you guys. Thank you for your attention. We'll see you next week.
I think we should like this.
Stop.